Welcome to an in-depth look at Markov chain password attacks, a sophisticated method used in cybersecurity. Unlike simple brute force attacks, Markov chains analyze character transition probabilities to make more informed guesses. These models are built from large databases of cracked passwords, representing how characters typically follow one another. Statistical analysis of word lists helps calculate the probability of character placement, aiding in quasi-brute force attacks. The model defines a probability distribution over character sequences, understanding common combinations like TH being more likely than TQ. Training the model involves breaking down real passwords into n-gram fragments and counting their occurrence frequencies. Once trained, the model generates potential passwords based on these learned probabilities, prioritizing high-probability strings. The cracking process begins by building a comprehensive password model from captured data, incorporating frequency patterns. Character transition maps are then used to optimize search sequences, especially for partially known passwords. This method is highly efficient because only the present state matters, reducing computational overhead and enabling scalable risk assessment. Markov chains significantly improve upon traditional dictionary attacks by training on general password rules. They also outperform rainbow table attacks in recovering a higher percentage of passwords. Compared to brute force, Markov chains are far more efficient, using a statistical model instead of trying every single combination. In real-world applications, these attacks are used in phishing to predict user clicks and in keylogger attacks to predict passwords. Popular tools like John the Ripper feature a dedicated Markov mode for these types of attacks. Hashcat also includes tools for creating Markov chain-based password cracking dictionaries. However, standard Markov models can generate repetitive passwords, which reduces their overall effectiveness. Dynamic Markov models address this by adjusting probabilities to avoid such repetitions. Enumeration-based models may also have lower cover rates for high-probability passwords and can be predictable. Even with complex passwords, predictable character frequencies can still make them vulnerable to these attacks. To defend against these attacks, always use a minimum password length of 10 characters. Ensure your passwords have complexity, mixing uppercase, lowercase, numbers, and special characters. Avoid common patterns like dictionary words, names, or keyboard sequences that are easily guessed. Utilize password generators for truly unpredictable and strong passwords. Employ security information and event management, or SIEM, and user and entity behavior analytics, UEBA, systems for attack detection. Markov chains also have broader applications in cybersecurity, such as intrusion detection. They can analyze honeypot data to predict attacker behavior and model security threats in cloud environments. Furthermore, they enable adaptive security systems to dynamically detect deviations indicating compromise. Markov chain password attacks are a significant threat due to their efficiency in guessing passwords through statistical analysis. Understanding these attacks is crucial for implementing stronger password policies and proactive security measures. Creating complex, random passwords that avoid predictable patterns is key to resisting these sophisticated techniques.